Okay, good afternoon everyone. So, I welcome you in the session after the lunch. I hope you had lunch and now it is a challenge for me to keep you awake for 1 hour or so. I will try my level best to make you awake, keep you awake. Okay, so I will be talking about the magnetoelectric effect in particulate and layered composites. I am really sorry for the experts, but this particular presentation I have made from the students' point of view, so that there are certain elementary terms also I have included, so that students should understand. Srinivasan sir is also here, but I am just for students' sake I have made this particular presentation. Just to give an idea, our group, the student, of course not everyone is working in the area of magnetoelectrics, but so broadly speaking, you are on this campus and you should know what are the opportunities or what are the different people they are working. So I just wanted to just inform you that on this campus there is Department of Physics, Department of Chemistry, Department of Biotechnology. Those are doing very good research in different areas. Those who have interest in the area of material science, they should visit the Department of Physics and Department of Chemistry. Major area where research work is carried out in these departments is basically related to energy applications. It may be solar cell, it may be catalytic systems, it may be hydrogen production, it may be dye-sensitized solar cell, or so in as far as the energy sector is concerned, it's conversion of non-conventional energy into the conventional form and energy storage. In Department of Chemistry, you have we have people working both in theory as well as experiments. There is a group working in the area of organic chemistry, inorganic chemistry, physical chemistry, analytical chemistry. So those things are there, and in Department of Biotechnology also very good kind of research work is going on. Sometimes you should take a tour and just get to know what people are doing. As far as our group is concerned, so I did my PhD in the area of magnetoelectric composites. So Professor Patankar Madam was my senior, and we worked together at Kolhapur. Later on, I joined at Pune University, and I got an opportunity to work with Srinivasan sir. So I spent about a year with him. There also I learned many experimental related things about the magnetoelectric composites in his lab, and now today I got an opportunity to give the presentation here. So in physics department we work in the area of development of different kinds of plasma systems, and it's used for materials processing. So whatever exposure I had got in the area of material science, so those and the potential of the plasma, now we are putting together to explore different opportunity properties of the material, and we are looking for different applications. These are some of the photographs. Now whatever work I am going to present here, it is basically from the thesis of Dr. Arif Sheikh and Dr. S. Prem Kumar, and the others are right now working in different areas. These are our collaborator. We sometime as and when we get an opportunity, we work with Srinivasan sirs. We have co-authored a couple of papers with him, and of course on campus also we have got collaboration. These are some of the glimpses of different kinds of research funding agencies, students, number of publications, and these are the research grant we could attract from the different funding agency, just to give an idea. So couple of postdocs are also working with us. These are the different patents based on the work at our department, and this is just to give an idea about the kind of work we do. the citation index and all those things. These are the some recognition received. Now coming to the business. Now you can see that multiferroics and magnetoids, these are very, like sir has introduced you to this particular topic, but just for the sake of completion I am just putting this particular slide. Now you can see the in ferroic, if you look at just different kinds of ordering, this ferroic, ferroelectric ordering, ferromagnetic ordering, so assume that you are a graduate student, BSc student, right? Am I right? Or no? Okay. So you are very well aware about different kinds of magnetic materials, and magnetic materials you have ferromagnetic materials, paramagnetic materials, diamagnetic materials, then you have antiferromagnetic materials, right? So these materials basically are categorized based on the alignment of magnetic moments. If you consider the magnetic, ferromagnetic materials, it has got domain structure, and magnetic movement in a domain structure is oriented in a particular direction, and such domains are oriented in a random direction. So that if you look at the net magnetization of the ferromagnetic material is 0, but if you just apply external magnetic field, the domain do get aligned in the direction of external magnetic field and you get some magnetization. And again, very well known examples of the ferromagnetic substances are iron, nickel, cobalt. These are as far as the elemental element or metals are concerned. Now this magnetism is not just related to the metals, but it is observed in certain oxide systems as well. If you compare like the metals and oxides, the oxides are more stable. Maybe I will throw some light on it so that you will get to know why the magnetism in oxides is stable, and I mean how you can get the magnetization for the oxide systems. So that is one of the key features as far as the development of these kinds of multifunctional materials are concerned. And on the other hand, like ferro, these words is something it comes into picture when you are dealing with iron kind of substances. But as far as the ferroelectric is concerned, there is no iron, but its behavior is analogous to that of the ferromagnetic material. In ferromagnetic material, you talk about the alignment of magnetic domains. If you consider the paramagnetic substance, there is no existence of domain structure, but the individual magnetic moment of magnetic moment of individual species is aligned in a random direction. Again, if you look at the net magnetization of the paramagnetic substance, that is also 0. If you apply external magnetic field, the magnetic moment gets aligned in a direction to that of the external magnetic field. Similar, analogous to ferroelectric and analogous to paramagnetic, there is there are materials called as ferroelectric and paraelectric. Ferroelectric have got electric domains, dielectric domains, which are aligned or which has got domain structure. So similar to that of the magnetic materials, if you apply external electric field, the electric domains get aligned in the direction of external electric field. And if you remove the external electric field, then there is some polarization do remain. Again, you are very well aware about the dielectric materials, like for example titanium oxide, TiO2. If you apply external electric field, the titanium oxide has got dipole, it gets aligned in the direction of external electric field, but the moment you remove, then the alignment is disturbed. This is not the situation when you talk about the system like barium titanate. In case of barium titanate, if you apply external electric field, there is a polarization. So the dipoles would get aligned in the direction of external electric field, but if you remove external electric field, some polarization remains over there. So this behavior is analogous to that of the ferromagnetic substance like iron, nickel, cobalt. So this is category of the material is called as ferroelectric material. Now you have to understand what makes material to have such a properties. Now the question is whether it is like all the materials have got this kinds of property. No, only certain class of material has got this kinds of property, and one of the category as far as the ferroelectric is concerned, that is what is called as perovskite. Perovskite again is a particular kind of arrangement. Again sir must have explained it, and I have also couple of pictures to make you understand what gives you ferroelectricity and what gives you the ferromagnetism. So as far as this particular slide is concerned, so what you have to understand, as far as the multifunctional materials are concerned or multiferroic materials are concerned, the material need to exhibit more than one kind of ordering. So for example, as I just explained you, ferroelectric and ferromagnetic. So here you can just have a look at it. In case of ferromagnetic, there is a hysteresis. Again, you must have studied the hysteresis. Hysteresis is what? Lagging behind. One of the parameter lags behind with respect to other parameter. As far as the ferromagnetism is concerned, when you go on increasing external magnetic field, the magnetization goes on increasing, but if you, so this way, if you remove this H, then when H becomes 0, there is some remnants. So this is what is hysteresis behavior. Similarly, for ferroelectric substances, when you apply electric field, there is increase in polarization. It goes to saturation. When you remove the electric field, some polarization remains. So this is what is the ferroelectric property. Now similarly, there is one what is called as ferroelastic and ferrotoroidic properties. So here also there are, I mean in short, if I have to explain, you are applying one kind of entity, because of that there is a change in other kind of entity, but the change in the other kind of entity is not retraceable. It follows some different path. So it gives some remnants over there. So this property, existence of such a property is very important. Now as far as the multiferroic is concerned, there is the existence of two or more ordering, and as far as this kinds of multiferroics are concerned, simultaneously the as far as more specifically the one category of multiferroic where the ferromagnetism and ferroelectricity do exist along with the ferroelasticity. Now the existence of piezoelectricity and magnetosection, this term I will explain in the later slides, okay. That gives you magnetoelectricity, and what is required here is a coupling between the two entities, what we are focusing on to get the magnetoelectric effect. Some historic background I would give you. So as far as the magnetoelectric is concerned, so it is electric polarization induced in a material by applied magnetic field. Now up to this time you must have got an idea. If you want to change the magnetization in the material, then you can apply external magnetic field. By applying external magnetic field, you cannot change electric polarization, right. But here in this specific category of the material, it is possible to change electric polarization in the material by means of a magnetic field. So that is what is the by means of magnetic field. Of course, you can change the magnetic property, but by means of a magnetic field, you cannot change the electrical property or electric polarization. More specifically, electric polarization I am talking about. So it is possible to change electric polarization by means of a magnetic field. Now this magnetoelectric effect is classified in terms of or this is observed basically two categories of material. One is a single phase multiferroics and other is two phase multiferroics. As far as the single phase multiferroics is concerned, the chromium oxide and bismuth ferrite, these are the very well known examples. Now I will not go into the details of physics behind why this kind of material gives you multiferroic property, but what you have to understand at this point is these are the material system which do have existence of ferroelectricity and ferromagnetism simultaneously, and it is possible to change the magnetization by means of electric field or the electric polarization by means of magnetic field in these kinds of material. So this is the multifunctionality. Now, if there is already materials are existing, why don't you use for certain applications? The problem with this is the existence of the signal or kind of signal what you get is not significantly high. It is very small. In principle, theoretically, whether you observe it, yes, observe. Practically, do you observe it? Yes, you observe it. But the magnitude of the polarization what you get or magnitude of change in the magnetization as a function of electric field what you get is not significantly high, and it is not suitable for practical application. Okay. Then what is the other option? Now, is it possible to take separately the category of the material which is ferromagnetic and other is a ferroelectric? The examples what I told is examples of the ferromagnetic substances what I told is iron, nickel, cobalt. Iron, nickel, cobalt, this is category of the metals, these are the metals. And the example of the ferroelectric system I told is barium titanate. Barium titanate is an oxide based system and it has got very high resistivity as compared to the metal. Now, there is a challenge to mix the two different categories of the material having wide change or vast change in the electrical properties, electrical resistivity. So, is it possible again in principle? Yes, Srinivasan sir has published so many papers on this particular aspect. He has found out the way out to mix this, but maybe in the later stage I will talk about it. What is easily doable and what is that many people have done, that also I will explain. But as far as the magnetoelectric effect is concerned, in if you just compare the magnetoelectric signal in case of single phase material and two phase material, it is significantly high in case of two phase material as compared to the single phase material. Now, so these are the some of the aspects which gives you the ferroelectricity and magnetic ordering in single phase materials. Now, I will be focusing more on composites. So, I will talk about the composites. Now, in case of composite, the kind of magnetic signal what you are going to get is going to be significantly high and it is going to be weak in case of single phase. Why it is so? That we need to understand first, and then we need to put forth the criteria, we need to put forth the requirement of the material to get significantly high magnetoelectric signal. Now, here what is used is magnetosection property of the magnetic material and piezoelectric property of the piezoelectric material. The ferroelectric materials are piezoelectric. Now you are well familiar with the ferroelectricity. Ferroelectricity is what, if you go on applying external electric field, there is a electric polarization. And as I told you that ferroelectric material do possess the domain structure. And if you apply external electric field, the domain gets aligned in the direction of external electric field. So, alignment of domain in the direction of external field not only changes the electric polarization, but also changes its physical shape. So, there is what you call as a piezoelectricity. In piezoelectricity, if you apply external mechanical force, then there is a polarization. Okay. Or if you like in this ultrasonic cleaner also, what is used? Have you seen ultrasonic cleaner in your laboratory, etc.? So, it produces the high frequency mechanical signal. So, there people use again the ferroelectric materials where those are subjected to vibration and it is going to give the mechanical signal. So, piezoelectric property of the ferroelectric material and magnetosection. Magnetosection is what, again, as I told you that if you apply external magnetic field, then there is a alignment of magnetic domains. See, again, alignment of magnetic domain is not just physical alignment, but there is also change in the physical dimensions of the material. So, if you consider the ferromagnetic substance and apply magnetic field, again with the help of some pictures I would like to show it. but this is what magnetosection. Now, so you try to visualize this particular magnetic effect in case of composites. Now, in case of the magnetosection material, the strain generated by means of external magnetic field, that is getting transferred to the piezoelectric material, and that results in the generation of voltage. Now, this Me composite can yield higher Me coupling. It is because of like the what you call, people call it as a product property. What is product property? The output of phase 1 acts as an input to the phase 2. So, depending upon the capability of that particular substance to enhance, you get the output signal. So, normally you people have used the two-stage amplifier as far as the electronics circuit design is concerned. In two-stage amplifier, what is done? Output of the phase 1 acts as input to the phase 2. So, if the gain is sufficiently high, you get higher amount of signal. It is something similar to that. So, here because of the change in signal to the phase 1, it gives some output, and that output acts as input to the phase 2, and that phase 2 gives some output. Okay. Now, this is particular figure what you can from this particular you can get an idea as far as the MEH means. Here the external entity what you are applying is the external magnetic field. So, if you apply the magnetic field, there is some change in the mechanical or there is change in the shape of the material, the material gets strained, and this acts as input to the phase 2, and you get the finally electric output. And the other is you can also apply the electric field. Applied electric field produces some changes in the mechanical shape and size of the material, that acts as an input to the magnetic material, and ultimately there is a change in the magnetic field. This is what is called as product property. Output of phase 1 acts as the input to the phase 2, and that gives you the better property. Okay. Now, this is the picture which will make the picture the idea clear. I am sorry, this is not you can see what you can see here, like if you apply the external magnetic field, there is a change in the dimensions of the magnetic material, and because of that the piezoelectric material which is present in the surrounding, that gets polarized, and that is how you get the output signal. The output of this phase or whatever change in the dimensions that is going to apply stress on to the second phase, and that gives the polarization. Now, here the simplest way to make the composites what? Just take one kind of powder, take other kind of powder, mix it, make the densify and make the composite structure. Whether the magnetic effect is going to observe in such a system? Yes, it is going to be observed. Now, this is first aspect what I will be talking about. Now, as far as the magnetoelectric effect in, as far as the magnetoelectric effect in phase 1 in composite is concerned, so it is very important to understand the connectivity aspect of in the composites. So, this is the one of the picture which is again published in the literature to make you understand the aspect of the connectivity. Here you can see these are the different cubes, the blank and the line cubes you can see. So, none of the blank cube has got is directly connected to the line cube. So, each individual cube is separate. This is what is called as 0-0 connectivity, and the amount of individual is also almost equal. So, there is one cube or one phase, and this another phase, one is a phase A, phase B, phase A, phase B, like that. There is no direct contact between phase A with another grain of the phase or another quantity of the phase. This is what is the 0-0 connectivity. So, here you can see it is a 0-1-0 connectivity. So, one type of cubes are connected 3-dimensionally, but other kinds of cubes are not connected, those are isolated. So, this gives you 1-0 connectivity, and in similar way, like you have different kinds of connectivity 0-0, 1-0, 2-0, 3-0, something like that. Now, if you go to the previous picture, this you can see. So, these are the different phases, the way in which they are connected with each other, that gives you different connectivity. Now, in the beginning I gave you the example of ferromagnetic substances iron, nickel, cobalt, which are typically metals. Now, imagine the situation, barium titanate, which has got resistivity of the order of 10 to the power 9 ohm centimeter, whereas the metals have got of the order of few ohms. And what is important for the ferroelectric materials is you need to align the ferroelectric domain in a particular direction. That process is called as poling process. If you are able to pole, or if you are able to align those domains in a particular direction, then the piezoelectric response of the ferroelectric is optimum, or you can get maximum. But if you are not able to pole them properly, then you do not get expected response. So, pooling of the ferroelectric substances is very important. On the other hand, if you mix the ferroelectric substances with some ferromagnetic substances like metallic substances, then what is going to happen? If the content of the metals is sufficiently high, then it is going to have the conducting path in between. So, if you apply external electric field, sufficiently large amount of current would flow and there is no polarization, sufficient polarization of the ferroelectric substances. And therefore, if there is no polarization, these piezoelectric properties are not sufficiently high, and therefore, you do not get the required signal, you are not able to observe it, and therefore, what is required? It should be optimum. And therefore, people have moved on to some other system, magnetic systems, which do not have the conductivity as that of the nickel, iron, cobalt. Okay. What they have done? They have used the oxide systems. Okay. So, I will be talking about it. So, connectivity in this particular composites is very important aspect, and it depending upon the consideration of the individuals, you can have different kinds of connectivity. Now, these are the typical pictures which gives you different kinds of connectivity. Again, Sir's paper has got mention of these kinds of connectivity. You can have different kinds of structure, this phase 1 and phase 2, like these particles are well dispersed, those are not connected with each other, and this is the matrix of some phase B, and these particles are phase A, let us say. So, phase A materials are well dispersed, this gives you 0-3 or 3-0 connectivity, similarly 3-1 or 3-3 connectivity, and this is very important aspect. As I told you that, like if you consider the piezoelectric substances like tablet of the piezoelectric substances, if it is attached to some metallic substances like iron, nickel, cobalt, then those are well separated, and therefore, the issue of the pooling does not come into picture if you go for 2-2 kind of phase connectivity. Now, for the design of the magnetoelectric substance, what is required is, see, properties of individual piezoelectric and magnetic two phase should be as high as possible, that piezoelectric coefficient and magnetic coefficient should be as high as possible. Phase compatibility at room temperature and high temperature should be there, and the piezoelectric and magnetic section material should respond properly to the external electric signal and the magnetic signal. And what is again one more important is, I just said that output of the phase 1 acts as the input to the phase 2, but while transferring the output of phase 1 to the phase 2, there is some losses, and sometimes these losses are very significant. Even though the signal is generated in as a output of phase 1, that is not getting transferred to the phase 2, and some special efforts are required to make or transfer of the signal generated from one phase to the other phase. Okay. So, these are the certain properties of the piezoelectric material, as I was talking about the systems like barium titanate. So, barium, this is kind of perovskite structure as I mentioned. At the corner there are atom, at the center there is atom, and at the face center of each there is one atom. And what is required to observe the field electricity is the non-centrosymmetry. So, in short, the non-centrosymmetry gives you the polarization. It is because the center of net positive charge and center of net negative charge do not coincide with each other, and that is why it gives some intrinsic polarization, and that gives you the external response to the external electric field as well. Now, this is unpoled sample, like these regions what you see, this is what is called as domain. So, in this domain the electric dipoles are aligned in a random direction. If you look at the net polarization of this kinds of system is 0, but if you apply the external DC electric field, the domains get aligned and here you get net polarization. So, this is important property of the material, and similarly, like as a function of external electric field, there is a change in the polarization as well as there is a strain exerted in the material. Now, these are some terms and terminology you need to understand the magnetoelectric effect. So, here the piezoelectric effect, it refers to accumulation of induced electric charges in a selected solid materials. Those may be crystals, certain ceramics, polymers, biological matter, DNA and various proteins. So, this particular property is observed in varieties of material, but as far as our research is concerned, we are will be focusing on the metals or ceramics, even not many polymers or some. So, metals and ceramics is our focus, and the polarization which leads to the change in the electric dipole moment. Now, you can see this is the picture. Now, if this is the picture when you do not apply any external electric field, suppose this is a dimension. If you apply external electric field, there is a change, an increase in the dimension. This is one possibility, and other is there is a decrease in the compression in the dimensions. So, as a function of external electric field, there may be change in the electric, there may be even change in the physical dimensions, that is possible. Now, this particular figure you tells you that let us consider sample in tablet form, where this is the tablet and the two plane faces of the tablet are applied with the electrodes, and typically the silver paint is used as a to take out the electrodes. So, these are the two electrodes. Now, here you can see there are three directions. Along the surface you can consider this as a x and y direction, along this surface x and y direction, and perpendicular to the surface you can consider this as a z direction, or you can designate this as a direction 1, 2 and 3. The direction is very important here to define different kinds of terms related to the ferroelectric materials. Suppose if you apply the external electric field in a z direction or in 3 direction. So, the directions are defined using 3 axes and labeled as 1, 2, 3 as shown in this particular figure. The polar or 3 axis is chosen parallel to the direction of polarization. So, here external electric field is applied along the 3rd direction. Okay. Now, these are the different terms which are frequently used. If you refer to research papers related to this, you will observe the term what you call as D33, D31, G33, G31, something like that. So, what these are? So, first of all, polarization vector, when the high DC voltage is applied to the electrode of the sample and arrow is pointing from positive to negative. Now, so these kinds of samples are commercially available as well. Now, these piezoelectric materials are poled, because in order to get optimum performance of the piezoelectric material, you need to pole it. So, poled piezoelectric samples are available. Now, how to recognize? So, if those are poled, some dot is put onto the, like if you have this IC74, have you used IC741? Operational amplifier IC you have used sometime for your any of the experiments? IC7, the students are asking, because this is basically for the students. IC741 is also 8-pin IC, and it has got one dot to identify the pin number where from counting should be started. So, similarly here the dot is put to check whether the particular sample is polarized or not. So, that gives you the direction of polarization. Now, piezoelectric coefficient is one of the important term which is used. It refers to the relation between input parameter to the output parameter. Use double subscript. What is double subscript is for? This first subscript denotes the direction of electric field and or electric for electric dielectric displacement, and the second subscript refers to the direction of mechanical stress or strain. As I told you that if you apply external electric field, there will be stress or strain in a particular direction. So, if you apply external electric field in a, let us say, direction 3, what would be the stress or strain in direction 3? That is denoted by, like for if you are talking about piezoelectric charge coefficient. What is the charge along direction 3 as a function of applied electric field in a direction 3? It is denoted by the letter D33. Once again I repeat. So, piezoelectric charge coefficient, it means like the charge displaced per unit area in response to applied stress. Now, if the applied stress is in the direction 3 and the polarization is also in direction 3, then it is D33. If the stress applied is in direction 3 and polarization is in direction 1 or 2, then it is D31. 1 or 2 is considered as isotopically equal, D31. So, as far as the design of magnetoelectric materials are concerned, these parameters are important. So, piezoelectric charge coefficient, where this is the equation Di is equal to Dij into Tj. So, Dij is a piezoelectric charge coefficient which has got unit of Coulomb per Newton. D is a dielectric displacement which has got unit of Coulomb per meter square, and T is the applied stress which is Newton per meter square. Now, similarly, like here as I was talking about D33. D33 relates the ratio of charge motion along the 3 axis to the applied stress along third direction. It is a D33. D31 relates to charge flow along the axis 3 or 3 axis to the stress along the axis 1 or 2. 1 or 2 are considered as equal. So, D33 and D31. So, this is about piezoelectric charge coefficient. So, here you are dealing with or you are interested in the charge, how much charge is accumulated along a particular direction as a function of applied stress. The other term which is important from the application point of view, that is what is called as piezoelectric voltage coefficient. So, piezoelectric voltage coefficient is the electric field developed in response to applied stress. Okay. So, the polarization or accumulation of charges is measured in terms of voltage. The polarization which is accumulated in a particular direction. Now, here like similar to D33, there is term what you call as G33. So, G33 is a piezoelectric voltage coefficient which relates the ratio of the electric field developed along 3 axis when stress is applied along 3 axis. It is a G33, and similarly there is one more, that is G31, so which again relates to the electric field along 3 axis to the stress along the 1 axis. Okay. Now, as far as the development of the materials are concerned, the piezoelectric behavior of the material in the linear range is related to the strain and charge. Now, the total strain in the material, in the piezoelectric material, is sum of mechanical strain induced by the mechanical stress and controllable accumulation strain caused by the applied electric field. Both these reasons are responsible for the total strain in the piezoelectric materials. So, similarly, the total charge accumulated on the electrode area is because of the electric displacement induced by the applied electric field and mechanical state. So, these are the mathematical equations which gives you the total state. So, as far as development of the magnetoelectric materials are concerned, the role of piezoelectric materials is very important. And in piezoelectric material, what is important is the stress strain and the displacement, dielectric displacement. And the strain induced is decided by these particular factors, and charge accumulation is also decided by these factors. So, where these equations in here, where this capital S is strain and SI is compliance coefficient, T is the stress, E is applied electric field, D is a dielectric displacement, and dKi is the piezoelectric charge and strain coefficient, where epsilon KL is the permittivity. Sometimes this epsilon K is also represented as a capital K sometimes. Again, different author use their own convention, but epsilon is very well accepted terminology as far as the permittivity is concerned. Now, the piezo ceramics with relatively higher piezoelectric voltage coefficient, that is G33 coefficient, those are desirable for sensor application. Now, we are focusing onto certain application. If you are looking for development of certain sensor application, then what is required? It should have higher piezoelectric voltage coefficient. Okay. And the enhanced value of the piezoelectric voltage coefficient can be obtained by tailoring both this D33 value and the dielectric constant of the material. So, it is possible to obtain high voltage sensitivity in this kinds of material. And for piezoelectric sensor, output voltage is open circuit, is measured in open circuit condition, and it is expressed using this particular equation. So, in piezoelectric sensor, this output voltage is basically depend upon D33, the applied stress and thickness of the sample. So, these are the parameters which are going to decide the applied voltage. Now, coming back to magnetosection. As I was talking about, magnetosection is what? If you apply external electric field, if you in a very simple way, if I have to tell, if I take a rod of iron and if you apply external magnetic field, then there is a change in the dimension. You may not believe that really that rod changes the dimension, but the changes are at very small level, microscopic level. So, ppm level changes are there, but those are very significant in the development of certain piezo sensor material. These kinds of materials are very important and interesting from the viewpoint of development of sensors and actuators. So, sensors and actuators are required for so many applications, okay? And it is very interesting to develop such kinds of material. Now, here is an example, like you can see here. So, this is the material, let us say the length of the material is L initially. If you apply external magnetic field in this direction, the length changes from L to L plus delta L. Why does it happen? Again, it is because of the alignment of the magnetic domains in the direction of external magnetic field. And these are the some equations which decides the magnetostrictive properties in the materials. Okay. Okay. As I told you that iron nickel cobalt kind of material, or there are alloy, iron nickel alloy, iron nickel vanadium alloy, iron nickel or aluminum nickel. So, these kinds of materials are very, so what is required as far as the development of such a materials are concerned from the application point of view? It is required that the magnetic material should give you significantly high change in the dimensions in response to small magnetic field. This is what is requirement. Of course, the materials which shows the change in dimension at higher magnetic field has got some other applications, but usually the material, even if you apply very small magnetic field, there should be sufficiently large change in the dimensions. The change in dimension is going to apply stress onto the neighborhood, so that the neighborhood phase gets strained, and as a result of the strain there is a polarization. and this polarization you can measure in terms of the voltage what is experimentally observed. Okay. So, both properties of the individual phase are important, and the metallic system, the limitation of the metallic system is overcome, like this is what is mentioned here, iron, nickel, cobalt, those have got the magnetic of 20. Okay, thank you madam. Magnetic which is of the order of so, if you refer back to this particular system, this one, so change in dimension is very important here. Now, such a change in dimension is of the order of 21 into 10 to the power minus 6 for iron, and of the order of 20 to 60 into 10 to the power minus 6 for this kinds of material. Now, there is one category of the material what you call as rare earth rare substituted iron and dysprosium system, typically terphenol and gulfenol kinds of system. Those have got this kind of value of the order of 2000 into 10 to the power minus 6, whereas this is 20 for iron, much higher. But again, their stability and their brittle nature, these are the limitations. The other category of the material whose magnetic is not as high as that of the terphenol or gulfenol, but sufficiently high, and it gives response to the relatively lower magnetic field. This category of the material is the spinel ferrite. So, the spinel ferrite typically are represented by the molecular formula MFe2O4. This is one of the unit cell of the spinel ferrite. I do not know whether you are aware of this kind of structure or not, but briefly I will just tell you that it in order to understand one unit cell of a spinel ferrite, you have to consider 8 octant at a time, and then you have to understand the alignment of the divalent. So, in this ferrite Fe is trivalent metal ion, M is divalent metal ion. Divalent metal ion typically iron, nickel, cobalt. So, these are the divalent metal ions are used, and O is oxygen. So, one unit cell of this kind of spinel ferrite consists of 8 molecules. This is one molecule, such kind of 8 molecules are distributed. Among this spinel ferrite, this cobalt ferrite has got very high magnetosection value. Now, people have succeeded in getting the value of magnetosection of more than 300 as far as the cobalt ferrite is concerned, whereas nickel ferrite as such has got low value of the magnetosection. Typically, even for the single crystal, this value is up to 25, 30 or 35, 40 into 10 to the power minus 6. However, if you look at, there is other parameter, that is what is called as the piezomagnetic coefficient. The piezomagnetic coefficient is the change in the length as a function of or for small change in the magnetic field. So, that piezomagnetic coefficient is sufficiently high for nickel ferrite, and therefore, if you just look at the dynamic magnetic response for the composites made using the the ferrites are basically ferrimagnetic. I just wanted to mention because you might not be aware of. Briefly, I will just give you an idea about ferromagnetic, ferrimagnetic and antiferromagnetic. These 3 category of the materials are important. Ferromagnetic substances are those where the magnetic dipole moment of adjacent species are aligned in the same direction. These are the ferromagnetic substances, and ferromagnetic substances possess the domain structure. Antiferromagnetic substances are those where the magnetic dipole moment of adjacent sites are aligned in a direction opposite to each other and opposite and equal, right. So, though if those are opposite and equal, the net magnetization is 0, almost 0, right. There is a third category of the material what you call as a ferrimagnetic. In case of ferrimagnetic, the alignment of adjacent magnetic species or magnetic sites is opposite to each other, but not equal. It is unequal, and this inequality gives you net magnetization. Okay. There are again different kinds of ferromagnetic substances, and all these ferrites are ferrimagnetic. So, in ferrites, the magnetization is basically decided by the alignment of magnetic moment of the adjacent species. Now, here the adjacent species have got equal and opposite, unequal and opposite, then you get some magnetization. But there are certain ferrite system like zinc ferrite, ZnFe2O4. In case of zinc ferrite, zinc is non-magnetic, and ion, magnetic moment of ion gets cancelled with each other. Therefore, it is expected that zinc ferrite in bulk form at room temperature is not supposed to be magnetic. Whereas, in case of cobalt ferrite, the magnetic, there is a term concept what you call as a cation redistribution. You may not aware about it, but again I just wanted to mention. In case of cobalt ferrite, the magnetic moment or the magnetic moment of ions do not get cancelled with each other. This is because the presence of the magnetic entity cobalt. So, cobalt ferrite it gives very high magnetosection. Similar to that of cobalt ferrite, there is what we call as a nickel ferrite. Nickel ferrite also gives you magnetosection, but the piezo-magnetic coefficient of nickel ferrite is much higher as compared to the cobalt ferrite, and therefore, it is interesting to study this kinds of system and study their magnetic property. Again, as far as the piezoelectric materials are concerned, the perovskite material, I have shown you the structure of the perovskite substances, which basically comprises of the atoms present at the corner of the cube, as well as the face center of the cube, as well as the body center of the cube, and their particular alignment gives you the piezoelectric property. Among the perovskite system, lead zirconium based perovskite system are very well known for their significantly higher piezoelectric performance, and that those are represented in terms of P84, P88. These are the different compositions of lead zirconium titanate, and as I mentioned that this D33 coefficient and the G33 coefficients and this dielectric constant, these are the important parameters, and of course, the tan delta is a dielectric loss factor. This should be as low as possible, and this is Curie temperature. Curie temperature is 1. Up to that particular temperature, the material is ferroelectric. Above that temperature, the material is transformed to the paraelectric. As far as the barium titan is concerned, the ferroelectric transition temperature is 120 degree, and therefore, if you heat barium titan kinds of substance up to 120 or above 120 degree centigrade, its ferroelectric properties are lost. Okay. So, this is what is the transition temperature, and whereas in case of lead based material, the transition temperature is significantly high as compared to the barium titanate. So, maybe I will go bit fast now. Now, all those are up to what I can take? 3, okay, another half an hour I can take. So, I just wanted to make you understand other results now is what I told, what I conveyed is what are the magnetoelectric composites, what are the expected properties of individual phases, and now how to choose those, or what is that people have already done and what are the significant results. So, there as far as the piezoelectric materials are concerned, there are again we are focusing on the perovskite kind of system. In perovskite kind of system, mainly there are 2 categories of the substances. One is a lead based. So, here everywhere you can see the PB. PB is as far as health issues are concerned, it is hazardous. Therefore, people wanted to avoid this use of lead in any of the substances. And there is other category of the material which is what is known as lead free. which is basically barium titanate. If you have seen the previous table, that if you look at the individual properties of barium titanate and compare with the lead based material, then lead based materials are superior. But barium the lead, because of the health issues, it is usually avoided. Therefore, the development of lead free as well as lead based materials both have attracted attention of the scientific community all over the world. And there is one third category of the material which also gives the piezoelectric properties, what you call as a aluminum nitride, zinc oxide, polyurethane. So, but again, if you compare the piezoelectric performance of among all these, the lead based materials are better. Okay. As far as the magnetoelectric substances are concerned, the metals like Fe, Ni, CO, they are alloys. The permanganate, again sir has worked a lot on this permanganate, gulfenol, semiphenol, terphenol. So, these are the substances, even med glass, these are the substances which gives very high magnetoelectric performance, but these all are metal based, and those which are made from the rare substances are going to be not easily available. On the other hand, these kinds of categories, spinel ferrite, have attracted a lot of attention. It is easily available, it can be fabricated very easily, it does not require very special atmosphere set or something like that, and it gives the better performance. So, these are the some of the reports in the literature, very old. This particular aspect started in 1888, and if you just go to the Google and just give the keyword or even go to the Scopus, you can see a lot of papers are getting published in this particular area, and a lot of applications are also seen. Now, as far as the there are two aspects. One is a selection of I am going to talk about two aspects. One is a particle composites and another is a layered composites. You may not be very much interested in other scientific result, but I would like to just give the glimpse of what you have to look in that particular result. I may not discuss those results in detail, but you will get an idea. So, as I was talking about development of particular composites, and I told you that nickel ferrite NiFe2O4 and COFe2O4, those are very interesting system as far as their piezomagnetic properties are concerned, and therefore, this is one of the system we have investigated in detail, and this is the lead based systems we have investigated. So, that is used as a piezoelectric phase, and the cobalt nickel ferrite is used as a magnetoelectric phase. Okay. So, these are the reports in the literature which gives you an again as far as the particulate composites are concerned. So, how particulate composites are made? In a very simple way, as I told you that take powder of one kind of system, take powder of other kinds of system. जैसा हमारा क्या रहता है सब्जी बनाते हैं ना, तीखा और नमक ले लो और मिक्स करो, it's kind of that. So, you take one kind of powder, take other kind of powder, mix it and subject it to the high temperature treatment. This is how you can get the particulate composites. Now, as far as the development of particulate composites are concerned, what are the questions to be addressed? The question to be addressed is which kind of distribution of the ferrite, that is a magnetoelectric phase, and ferroelectric, that is the piezoelectric grains, exist in ME composites. The aspect of connectivity, how these two phases are connected to each other. So, this is one of the aspect which is going to decide the performance of magnetoelectric composites. What will be the effect of concentration of individual phases on the microstructure? Which type of microstructure is more suitable for getting higher magnetoelectric signal or coefficient? What is the relation between the connectivity with the resistivity, ferroelectricity and magnetic voltage coefficient? And what will be the effect of porosity on the ME coefficient? So, these are the some of the fundamental aspects which one should understand as far as the development of the magnetoelectric composite materials are concerned. Now here this is the recipe. I will not go into the details. So those who are interested I can just explain them. This is the characterization. Again, I don't know whether you are aware of about the characterization technique. I hope no. Have you done any characterization work, students? Naina? Some of 50%. Okay, okay. So this is one of the very popularly used technique to characterize. So these are the okay. You might not have studied in detail, but at least you must be familiar with the Bragg law. Are you familiar with Bragg law? Yes, is it? No. Bragg law is something related to crystallographic structure, or like whatever materials are existing in nature, those are categorized mainly into one among the 7 crystal systems. There are total 7 crystal systems. So whatever material either the material would be amorphous or other material would be crystalline material. The crystalline material means what? It has got regular and periodic arrangement in 3 dimensions, whereas amorphous means what? There is no regular and periodic arrangement. Now, if the arrangement is regular and periodic, then it acts as a crystal griting. You must have used the in your optics lab, you have used crystal griting. Griting is it has got so many slits and you have some source, there are slits drawn and you study the diffraction. It is similar to the crystallographic structure acts as a griting for the X-ray. In optics lab, you use the optical source like sodium source or to certain extent mercury source, but not for diffraction. To study the diffraction, you use sodium source, and you have crystal griting. You impose the light and study the diffraction pattern. So here the crystal acts as a griting, but it has got the dimension of the order of angstrom, and therefore you have to use this to study the diffraction. You have to use the source of similar kind, and therefore X-ray is used as a source to impinge on it, so that it gives you an idea about the structure. So if you record a particular X-ray diffraction pattern of particular system, you get the fingerprint pattern. You understand fingerprint pattern is one with the help of which you can identify whether that particular person is there or not. Fingerprint is used to identify whether that belongs to which person. It is similar to this. So if you record X-ray diffraction pattern of cobalt ferrite, this fingerprint pattern you will be getting, and similarly for others also you will be getting. If you change this concentration of nickel and cobalt, there is slight change in the position. Is because of the change in the dimensions of the cobalt ion and nickel ion. But this is again very very well known technique used. Similar to that of the ferrite, this piezoelectric also has got fingerprint pattern. Whether it is going to produce fingerprint pattern or not, to confirm that, detailed crystallographic analysis can be done in a separate way, but this is one preliminary investigation you can do. So to make the composites, this is the microstructure of the cobalt nickel ferrite, one of the representative image. This is the microstructure of lead manganese niobate titanate, and this is the microstructure of the composite. What you see here is there are certain white grains and there are certain black grains. This is recorded in backscattering mode. So this gives you an idea about the kind of connectivity it has got. Now the connectivity analysis, I can show some of the pictures which will make you clear. So these are the certain other detailed investigation we did. I will not discuss this. So again, this is the X-ray diffraction analysis, stain analysis. Again, I will not go into the details. These are the some of the points you get an idea from the X-ray analysis. This is important. So here this is the image recorded in the secondary mode, whereas this is the image recorded in the backscattered electron mode. In backscattered electron mode, you get an idea about these are the white grains and these are the black grains. From here, what you come to know, two kinds of phases or two kinds of grains are distributed. Now, you have to understand what are these two, why one is looking black and why other is looking white, and what are the elements present over there. Now, to understand that, we did elemental mapping on this. So, here you can see, as far as the ferrites are concerned, spinel ferrites are concerned, what is the major content? For example, NiFe2O4, if I consider, the major content is iron. The grain which has got iron as a content should belong to ferrite. On the other hand, this lead magnesium niobate, and in that case, lead is the major content. So, the lead is not common to ferrite and iron is not common to ferritic. The grain where iron is present, it belongs to ferrite. The grain which belongs to where lead is present, it belongs to ferritic. That is how you can find. Now, here we did the elemental mapping, and this based on this elemental mapping, what you come to know, for example, this is the PB, we did the analysis for PB, and you can see in these regions, here, these regions, you can see this is lead, and what it belongs to? It belongs to white grains. And iron, if I consider iron, this is iron. So, here is iron. Now, you can see the black grains belongs to iron and white grains belongs to lead. Now, it is further interesting to understand the what way they are distributed. Now, here the aspect of the connectivity comes into picture. Now, here you can see, as I was talking about the 3-0 connectivity. 3-0 connectivity, the matrix is made up of one kind of substances and the other kind of substances are very well separated. So, this gives you 3-0 connectivity. This is going to happen when I mix about 15% of the ferrite phase with the 85% of ferritic phase. So, major is one kind of phase and minor is other kind of phase. So, this gives you connectivity. So, depending upon the type of connectivity it has got, you get specific property, and again by changing the concentration of this ferrite, we did the analysis of the kind of connectivity these particle composites have got. So, this you can see here you have different kinds of connectivity, 3-0 connectivity and 3-1 connectivity, something like that, right, and this is going to affect. Now, density is another parameter. We expect these kinds of composites totally packed, but actually we get there are some pores inside, and that is going to affect the performance. So, again we did the density analysis. This is the density variation. As far as the connectivity is concerned, you get different kinds of connectivity, 3-0, 3-1 and 3-3 type of connectivity. This is the dielectric response of the substances. Again, in the interest of time, I will not go into the details why this particular behavior is there, etc. But this is the again the characteristic property where you get peak in the dielectric measurement, and this is for the ferrite. In ferrite also at transition temperature you get the peak, and this we have done it for the composite systems. We did some detailed analysis again. So, this is part of the detailed analysis. So, the kind of connectivity what you are going to have is going to affect the resistivity. Resistivity is one of the important aspect. So, 3-0 connectivity gives you higher value of the resistivity, whereas 3-3 connectivity resistivity decreases. This is other detailed analysis. This is also going to affect the kind of the connectivity is going to affect the ferritic performance of the substances as well. So, what is required to have such a material as a magnetoelectric materials? It should have both ferroticity and magnetism, and this is the proof of what the composite what we have made has got both the kinds of ordering. This is the detailed analysis. It has got ferroticity as well as the ferromagnetism, and the connectivity plays an important role. And this is the magnetoelectric response of what is here. What you have to understand is the magnetoelectric performance is recorded for basically two directions. One, this is the sample. If you apply the external magnetic field parallel to the surface, we have designated this as a transverse mode, and if it is applied in direction perpendicular to the surface, then it is designated as a longitudinal. So, longitudinal and the transverse response is different for this kinds of composites, because in case of longitudinal magnetoelectric performance, the demagnetization factor becomes prominent, and therefore the response becomes that diminishes. So, this is the response what you get. Basically, for composites having 3-0 connectivity, we could get higher performance. This is the magnetoelectric performance of the typical system, and this we have done for even for other systems as well. Now, this is what I was talking about, piezomagnetic coefficient, that is the change in the magnetosection as a function of change in magnetic field. So, this should be higher for the better performance of the material. This is what is required, and this is the slide which gives an idea about the resistivity and the ME coefficient and connectivity. So, in nutshell, the sample having 3-0 connectivity gives you the better performance as far as the particular composites are concerned. Okay. This is the slide which gives you an idea about the role of porosity. So, porosity should be also as low as possible, because you can see as porosity increases, the performance ME performance keeps on decreasing, both 3.3 and 3.1. So, porosity should be as low as possible, but I think that even the porosity should be there at optimal porosity would facilitate the ME performance. This is what I think. So, this is what is the total glimpses of the result. 3-0 connectivity provides you better work, and this is what. Now, just quickly I will just go through the slides, just flash forward. One aspect is we focused on is a particular composite, and other is layered composites. Again, I will not go into layered composites. So, you have to make tape, or you have to make one phase maybe in the form of pellet and stick it on with the other plate. So, this is what you can do, depending upon how you are applying the external magnetic field and what is the direction of polarization. The composites are named as a transverse or longitudinal or transverse longitudinal, like that. Now, here what is the different aspect what we tried is to get higher value of G33 for the, again I will not go into these details. In composite what we did is we have made the layered composites of the space LZT, this is another system, and as far as this particular system is concerned, it was kept constant. Now, here these layers are electrically parallel with each other, but mechanically in series with each other, and therefore, you get improved performance. See, as far as the miniaturization of the device is concerned, what you need is very thin device, but if you go on thinning the device, the piezoelectric performance is diminished. Now, how to compensate this is to make the layered composites. In layered composites, this is the way what we tried. So, where the different kinds of electrodes are, this arrangement what we made. And yeah, so this is the picture you can see. This is the picture, the schematic of the device what we have made, and this is the diagram where you can see these two are electrically parallel and all these are mechanically in series with each other. This gives you higher piezoelectric performance. Okay. So, this aspect we use, and again this is detailed, this one, this is a detailed characterization we did, the experimental setup, again the detailed characterization we did even the polarization and the displacement analysis, dielectric measurements, all this is the detailed analysis of this kinds of systems. Variation of dielectric constant as a function of temperature, typical at transition temperature you get this one. Now, what is interesting to show here is the kind of microstructure we could obtain. These are the sample. These are the self-standing tape we have made using the tape casting method, and those were stuck onto each other, and these were co-sintered to get the final response. Now, these are the pictures of the microstructure. We have put the platinum paste onto this. This is this is unsintered and this is the sintered electrodes. Now, these are the detailed characterization. So, here you can see like as a function of sintering, this is the this for nickel zinc ferrite. Again the detailed analysis of the nickel zinc ferrite. This is the structure what we wanted to prepare. Here you can see this is how the layered structure we have made with the help of this one. Now, and this is the composite structure. So, this is the PSLZT layered structure, and this is the nickel zinc ferrite, and this is sintered for 2 hours. Again sintering time also we have optimized and its performance was checked. Again the detailed analysis we did. Here you can see this green region is for iron. Again it is obvious because of this is the ferrite structure, and here the picture of the composite structure you can see, and these are the final samples what we could get. We did some magnetic force microscopy and piezo-magnetic force microscopic analysis. These are the detailed characterization of this. Of course, we did some DFT calculations also on this that I have not presented over here. So, this is the resistance recorded as a function of frequency, and you get the resonance peak at particular frequency, that is the axisymmetric mode of vibration. And this is again ME performance of this. ME performance of the layered structure is much improved as compared to the particle composites. Again the magnetization behavior, and this is the magnetization behavior, this is the detailed analysis. Okay. So, here the axisymmetric mode that was sintered at different time, and finally it gives the ME coefficient of about 6 volt per centimeter per oerstate at resonance. So, these are the structures we could develop. So, these are the laboratory made. This is the bulk, that is the particle composites, and whereas these are the co-sintered composites, it gives much better performance. So, this is the summary of the work what we could get. I think this has stuck. We have also tried a device based on this, which is able to. So, this is this gives its ME performance because this is the nickel zinc ferrite. It gives its performance at relatively weak or smaller magnetic field. So you can call it as a self operating device, self bias devices also. So these are the some of the points what we could get. So what is point to be told is that we could get the 6 volt per centimeter overstate at low bias field of about 25 overstate for this kinds of structure. This is what we want. So with this, I welcome if there are any questions from students. Any questions from two theta position will be different for cobalt ferrite and for nickel ferrite. So if it is not single phase, nickel ferrite mixed with the cobalt ferrite, if it is just composite, you are supposed to get peak broadening. One has got the lattice parameter of 8.39 or so, and 8.34 and 39, something like that. So because of this difference, you get, if you do high resolution X-ray diffraction, you get two different peaks if it is not single phase, and if it is single phase, you will get only single peak. And in case of composite, you get signature because of both. The signature of both individual phases remains intact, and you see its signature in the composite when you record the X-ray diffraction pattern. Any other questions from you?
So, have you used any other techniques also to make composites other than tape casting?
Particulate composites we have made, we have used.
Layered,
For layered, actually we have used the glue stick.
so
That we
is
did.
there a comparison between two?
Yeah, the co-sintered what we have got gives better performance than the glued one. That is what.
So tape casting is superior.
Tape casting and co-sintered, but this is tricky, I would say. Getting this kinds of composite warpage free, crack free, is you have to really optimize the parameter. Maybe sir maybe can make some comment on. So glue one or co-sintered one. Co-sintered one would give you better performance, but it is tricky. Make use of glue is very simple. Whatever is phase, you just stick, you will get some performance. Any other comments, questions from the students? The detailed research result I have not discussed in detail. Huh?
For barium titanate, you say QE temperature is about 120 degrees Celsius. Is it for bulk or nanoparticle?
Bulk. Nanoparticle, have you seen any change? Have you done? Huh? You don't really expect much change because you don't go to that small size where you really expect some change. Of course, there might be some change, usually it is observed, but the kind of system what you are working on, I do not expect very significant change because you are using some chemical methods. Typically, the size is of the order of few tens of nanometer, and there I do not expect any significant change.
So for porosity,
Ah.
you say for magnetoelectric we need less porous materials. I am working on nanometer. I have read some papers. They say we need more porous material as well.
Which system?
For nano generator, I am working on nano generator.
Nano generator.
They say we need more porous material in order to get better.
Usually, if the structure is porous, then whatever signal is generated, it is going to be lost right? But if the porosity, that needs to be investigated, if the porosity is optimized in such a way that whatever signal is generated is effectively transferred or passed to the second phase, then it may be possible, right? Anybody, madam, want to say something?
Particulates will prepare
Huh.
with a different weight percentage. Like which is suitable to get high AME?
The three
80% ferroelectric, 20% ferromagnetic.
ferrotic should be higher.
In that case, that can we expect that is an AME response or as a piezoelectric response?
ME response is good, means piezoelectric is also good, because piezoelectric response depends upon the way in which you pole the sample. If you are able to pole the sample properly, you get good piezoelectric performance. If you are not able to pole, then you don't. If you have some other phase which has got higher conductivity, then that doesn't allow full polling of the sample, and therefore what sir has tried is to make two layer composites. So you take some complete phase of piezoelectric and stick magnetorestrictive phase onto it with the help of glue. So that gives better performance, even though the resistivity of the magnetorestrictive phase is not very high. That works because that doesn't hinder the polling of the piezoelectric sample. Yeah, that way you can get to better. Particular composites, no, that doesn't work. For particular composites, it should be, I mean, the ferrite has got resistivity of the order of 10 to the power 6, and whereas ferroelectric have 10 to the power 9, 3 order of difference is there. Because of this 3 order of difference, the pooling is hindered, and therefore, for 3-0 connectivity, you get better performance. But if the connectivity changes from 3-0 to 3-1 or 3-3 or something like that, the performance diminishes, decreases. Any other questions from any of the students or something? Now this Dr. Ashwini Datar also did her PhD in the area of magnetoelectric composites. Deepali is working, and that Shankar is also working. Deepali has almost finished, is working in the area of the magnetoelectric composites. So, I mean, later on also you can interact with these people to get more insight about the field. Okay. Okay. Yeah, okay. If there are no more questions, so I'd like to, if there are questions, you can ask the questions.